Okay, everybody, I'd like you to take a look at this video that explains an important problem that I think is useful for understanding a lot of important concepts about sampling. Okay, so this is from the Orphanitis book. It's example 1.47, and there's sort of a lot to it, and so I wanted to make a video that you can go back and look at in case you are fuzzy about some of the concepts. All the concepts are here in this example written out in the textbook, but I wanted to have this video to add on to help clarify some of the important points. Okay, so the basic idea is important to understand. All right, so we're going to start with a sound wave that has a certain form. Okay, and part of the thing you should notice here is that T is in milliseconds. Which if you think about it, if T is in milliseconds, that makes frequency in kilohertz, because there's a reciprocal relationship between time and frequency. Okay, so when I look at these terms here, I can identify the frequency components. This is 10 pi t, so 2 pi times 5, this would be a 5 kilohertz term, 15 kilohertz term, 25 kilohertz term, 30 kilohertz, 45 kilohertz, and 125 divided by 2 kilohertz. All right, so we can identify those, and then part of the point of the problem is to classify the components of the signal as to whether they're audible or not. All right, and so if you have really good ears, you can hear up to 20 kilohertz. All right, so there are portions of this that are not audible. All right, so if I would put those in red, all right, you can't hear this term, you can't hear this term, or this term. So the first two terms of this waveform you could hear as tones, and the rest you could not. All right, so the idea here is we are studying sampling of sinusoids because we know a real signal is composed of a continuum of frequencies. So if we can understand what happens to specific tones, that gives us a lot of intuition about what happens with sampling. All right, so the sampling process is going to be, so tracing through the steps, first of all, we're going to pre-filter, then we sample at 40 kilosamples per second, and then we reconstruct. There's no other processing in between, so ideally we'd like YA of t to match X of t. All right, but we're not sampling fast enough, so that's not going to happen, and we want to look at the consequences of that. All right, so hopefully you get the setup one more time. There's an audible component of the signal. There's an inaudible component of the signal. We really don't want that inaudible part to be there, so because we're only caring about what the signal sounds like. And so ideally we would filter this out with a pre-filter and then reconstruct, and in the ideal case we would only get the first two terms. All right, so he breaks this up into three different parts. First of all, what happens when there's no pre-filter? And then second of all, what happens when you have a perfect pre-filter, an ideal pre-filter? And then he makes it more practical by saying, all right, we're going to have a pre-filter. It's not going to be perfect. It's going to fit this specification where we're at 0 dB up to 20 kilohertz, right? So notice that 20 kilohertz is Fs over 2. All right, and then the filter starts to attenuate from there. All right, so it's not a perfect filter, and that's an important part of this problem. All right, so that's part C. Okay, so moving through the book here, all right, he identified the frequency components like I had already done. So we know these two terms are audible, and the rest of these are not. Okay, and this is what we'd like to see at the output. All right, and then he says, okay, let's think about these in terms of frequency components, and we know that cosine has this transform that has spikes centered at the frequency of interest. So here's FA, and here is F minus FA and F plus FA. So what we start to see here is the spikes indicating the energy component in frequency. Okay, so let's clear that off. All right, we have lots of things here. A through F, we have all these signals, and he has this graph of placing things in the frequency domain. Okay, so what we know from sampling is the only thing that we're going to keep after we do reconstruction is the component that goes in the Nyquist interval. So if we're sampling at 40 kilosamples per second, the Nyquist interval is minus 20 to 20 kilohertz. All right, so those would be the only things that should show up at the end. And of course, because we don't have a pre-filter, all these other components are going to alias. All right, and we talked about that already in class. If we wanted to calculate the alias frequencies, we look at the ones that are undersampled. All right, we're good with A and B because those were sampled at a fast enough rate where they're not going to alias, so we can keep those original frequencies. All right, so the next thing that's done, and I want to make sure you understand, each of these components is alias to a different frequency. All right, and so we talked about that. You take 25, you start subtracting 40. When you subtract 40, you land at minus 15. That's inside the Nyquist interval. You are done. Okay, same thing with 30. 30 minus 40 is negative 10. Okay, 45 minus 40, you're in the Nyquist interval. You're done. All right, but this one, 62.5 minus 40, you're at 22.5. That's not quite in the Nyquist interval, so you have to subtract again. That's why there's a 2fs here, and we land at minus 17.5 kilohertz. Okay, so in the case where you don't pre-filter at all these terms made it into the sampler, and so they're going to show back up in the output of the reconstruction filter. Okay, he didn't have a picture of that. All right, so here we go. We have the first two components. Those are good. Those didn't alias, but then the C component at aliased here to minus 15 kilohertz, the D component minus 10, E component 5, F component minus 17.5 kilohertz. Okay, so you might notice that this whole expression simplifies, because if we look at this 2 pi 5 term, that's the same thing as cosine 10 pi t, so the E and the A term combine together. So that simplifies things a little bit, but A is part of the audible part, and E is a distortion that's coming from aliasing. Same thing's happening with B and C. Those terms are combining, and then you have separate, now audible terms that come from components D and F. All right? So the bottom line is this would not be a good thing to have happen if we were worried about the fidelity of the audible part of the signal. All right. So that takes care of part A. In part B, all right, in part B we're looking at filtering. All right, we have an ideal filter. The ideal filter response, I'll trace that in blue, is a perfect filter with perfect attenuation. The A and B components get passed through. Everything else gets zapped out to zero. Okay, this particular problem is really easy because, if you think about it, what happens is each component is filtered. All right, so I'm going to highlight the filter terms. You have the filter from frequency A, frequency B, C, D, E, and F. These are not alias frequencies. These are the actual frequencies that show up at those frequency components. All right, so in this particular case where we have an ideal low-pass filter, all these beyond 20 kilohertz, these are zero. these get zapped out to 0. All right, and that's good. Another thing he makes a note of is that actually when you apply this to a realistic filter, there's always going to be a phase component of a realistic filter. So that would show up right in here. But if we're looking at magnitudes, we can draw some conclusions. And so basically, he assumes this part is 0. Okay, it's an oversimplification, but you could actually add that back in if you wanted to. All right, so the conclusion from part B is good, that we only get the audible part back if we have an ideal pre-filter. Okay, the next part, though, we start worrying about, well, what happens if we don't have an ideal filter, we only have a filter that starts to attenuate at certain frequencies. Okay, and so to redraw that picture, he had the filter was 0 dB, no attenuation, and then you start to attenuate at 60 dB per octave, all right, at 20 kilohertz. Okay, so the question becomes, how much attenuation is there for every one of these components, okay, that are outside of the passband of the filter? So we know that A and B are good. Those are in the passband. Those don't get distorted at all. That's what he's saying here. Next, we need to look at how far away from this roll-off frequency, Fs over 2, in this case is 20 kilohertz, are we at any given frequency? Okay, so we see here at 25K, we're calculating how many octaves. Okay, so octaves are log base 2. All right, so you do log base 2 of 25 over 20. If you are rusty on how to calculate that, that would be 25 over 20 natural log divided by the natural log of 2 will give you the base 2 logarithm. Okay, so we see we're not a full octave away, 0.322. Octaves are power of 2, right? And we can go through here and calculate how much attenuation you get with each of these frequency components. All right, so just plugging into that formula, these are the number of octaves. All these would be some fraction of an octave or multiple of an octave. Okay, and because we know the attenuation rate, then we can figure out, oh, the C component has 19.3 dB of attenuation, the D component 35.1, and so forth and so on. So we can work out all those attenuation factors. Okay, and then we know the definition of dB. All right, so we essentially undo the take the inverse of that, and so we can calculate the actual linear attenuation factor, not the attenuation factor in dB. Okay, so we plug in each of these attenuation factors and we get a corresponding attenuation that's linear, not in dB. Okay, so moving forward, what that tells us is that in the output here, okay, let me make that in blue, we get the original audible part, okay, and then we get some parts that are, this is the output of the filter, that are attenuated, okay? So now we go through this same process that we did before. We sample and alias, and instead of having 2C and 2D and 2E and 2F as the amplitudes, we have these reduced amplitudes on the parts that alias, okay? So when we go through there, there's some details in the calculations that you can easily do, but you attenuate you alias all the frequencies and you come up with an output that looks like this, okay? So after sampling and reconstruction, everything here is less than 20 kilohertz, all right? And we identify what are the alias components, all right? So here's E, that's an alias component, but instead of just E, we have E divided by 3,234, all right? So E will be much less noticeable. In fact, I would argue you can't notice that, All right. C, it's only divided by 9. That's an alias component. It's only divided by 9. It's better than not dividing by 9. All right, so the previous result was just C, not C divided by 9. And the D component is divided by 57, and the E component would essentially be negligible. All right, so that gives you the idea. We are looking at how a pre-filter helps us in terms of accurately representing a signal.